I didn't want to have to restart everything. But
but now we're patching off now.
okay, good. So, let's see. I imagine it's going to work now. Good.
Yeah, nice.
It's unfrozen. Right, I'm from here. It's very nice. This is actually a dive site. Quite a good one. It's Japan, but subtropical. Very different history. And this university, our university, was inaugurated in 2012. I joined very slightly, well, basically a year before that, helped them set it up. We're now at about 100 faculty-led research groups, and that spans all the physical and life sciences. So it's small compared to, say, Lund University. We have a 5-year PhD program with 300 students. So we are a university, we do teach, but we don't have undergraduates, which makes it a very different experience from, say, being in Bristol. And we have a very LINXS-like visiting program, which in fact I was responsible for setting up. And what's most unusual about our visiting program is that, like the university, it covers all the physical and life sciences. So everything, essentially, which brings many opportunities and a few challenges. So here's the visiting program. That's our cozy coffee area. It's a bit like yours. This one's got AV installed, so it doubles as a meeting and seminar space. We have a lot of blackboards, which theorists like me can get excited about. And we have visiting scholars, thematic programs, domestic visitors, quite a lot of events. We routinely record stuff and find it on YouTube. That's what I would maybe have been attending if I'd been there today. Also on hybrid and on Zoom, so you'll be able to download this should you be interested in general asymmetry of some kind. Okay, so yesterday I had a rather fun private tour of the ESS construction site, guided by this woman in appropriate safety equipment. And we were looking at, this is part of the beamline, the C-spec, which is going to be an inelastic neutron scattering instrument of fairly high specification. I understand the detector designs evolved a little. This is Pascal standing next to the tank that's going to be full of helium to catch the neutrons. So that's kind of fun to see it coming together. And if you don't already know, inelastic neutron scattering works a lot like this. You fire a neutron, the target, it scatters off the target. The target, which is some quantum material, in cases I'm in work on, absorbs some energy, there's some cross-section, and you end up with a very, very pretty picture like this that tells you how energy was absorbed, how much energy was absorbed, or what energy energy was transferred as a function of wave vector. And you can then, well, it's a very reliable source of pictures, but also an enormous amount of physics information about what's going on inside the system. So if you want to interpret one of these pictures, you go to the data expert on neutron scattering. This is the first one I encountered. And then this one, I was written on that. And in there, you will find an equation which links this cross-section to the structure factor. You have to remember to project out some stuff. That would be so important today. And what you then need to do to interpret it is to stick some sort of modeled calculation in there. So this data, this is like Rydbergs. It's an antiferromagnet. We understand most of its properties pretty well. We know how to write down and parameterize a model that gives a totally convincing fit to this when you calculate sufficiently carefully. It's a recent paper by a student in Lund. So that's all good. But in this case, to be honest, you can read off the physics from the picture. You know that you're looking at a spin wave, a neutron has flipped, exchanging one unit of angular momentum, spin one, with the spins in the system, and that creates a sharp peak. So the excitations are spin one, excitations are spin. Okay, so what don't we understand so well? The those are always the things we're most interested in, right? So quantum spin liquids are a kind of holy grail for condensed matter physics. They're a thing we seek, not always successfully. And we're very excited about them, essentially because they are the most quantum phase of matter, or a very pure form of a very quantum phase of matter. So they do a lot of things that you don't normally find in magnets, like I say, that in Ducray. They are very highly entangled. I'll say a lot more about what that means later. And they have fractionalized excitations, which means to say that when you hit them with a neutron, you don't just create one spin wave, you may create an infinite hierarchy of other particles that haven't been seen before, quasi-particles. However, there's a problem. Candidates come along refreshingly frequently these days, at least once a month, I would say. And somebody does a neutron scattering experiment, and they get a pretty picture, and they write a discovery paper, often in a good journal. They say there's no magnetic ground peaks, it's not magnetically ordered, it's got a continuum of excitations. I found a spin wave. Very good. And then about a year later, somebody writes a paper saying, "Nayam, in fact, what you found is a really dirty sample, and everything that you've seen is a consequence of disorder, and it's got nothing at all to do with exotic, beautiful quantum physics." And as an example of that, well, this fact we'll come back to, what makes them interesting in doing this. Here's a triangular lattice spin half, or pseudo spin half magnet based on a turbulent free class. Here's the discovery paper. Hooray! We found a quantum spin liquid. We're in Nature Physics. And these correlations that they measure in experiment, they're explaining in terms of quantum fluctuations, and that looks kind of convincing. And here is a couple of years later, a paper by some hard-nosed theorists who say, "No, you haven't. We've done a more serious calculation than you, and put the effects of disorder in, and we've got something like this, but it's lost nothing at all." And if you just look at those pictures, you'd find it impossible to say, well, is that theory better than that theory? There's certainly a lot more work gone into this theory. But with the absence of other information, all you can really do is compare the pictures and say which one looks more like the data. So is there another way of looking at this data, same experiment, but interpreted differently, that would give us a better way of answering this question? Spin liquid versus disorder. That's really the question for today. And to address that, we need to think about what makes quantum fluctuations special in the first place. And that takes us back to the early days of quantum mechanics and this word entanglement. So a bit more about what entanglement is. But it's become relevant for our community because some of the measures of entanglement that have been lying around for a while in quantum information community have now crossed over in people experiment. So this is quite a nice paper. They wisely chose an extremely well characterized system, spin chain, where we know everything. There's the experimental measurement of the dynamical structure factor. It's so well parameterized, you can really calculate everything in theory as well for the system and get identical numbers, more or less, for the structure factor. They looked at a measure of entanglement pairs of skins called concurrence. Actually, this is the two-tangle, it's basically the same thing. That really didn't work so well compared with simulation. And they looked at a measure of entanglement of many spins. This is quantum Fisher information, and that would pretty well. So the idea is out there. Can we apply this and get it to work on spin liquids and maybe resolve some of these cases where it isn't quantum spin liquid? So can experimentally accessible measures of entanglement be quantum spin liquid disorder different states? And I will tell you all the answers now. I may well run out of time later. So at least in the cases that I'm going to tell you about, the answer is yes. If we look at the quantum Fisher information, we see a power law behavior in the quantum spin liquid and an exponential decay in the disorder-driven state. As long as you have enough information over a wide enough range of temperatures to distinguish those two things, that tells them apart. So yes, in some cases. But as usual, there's a ton of traps you can fall into, and some of them have already been formed. What do we need to understand? Okay, so these are the things that I will tell you if I don't run out of time. Why do experimental results in two-tangled in the spin chain differ from simulations? Is it safe to rule out a random singlet phase or perhaps multi-party entanglement? How should we interpret the power laws in the experiment? What's this scaling collapse mean? And the answer is, well, this is a totally unreliable witness. In fact, give up on concurrence. Message. No, it is not safe to rule out entanglement. Random single states based on multi-party entanglement. In fact, with everything, it turns out to have some depth of entanglement. The power law is very meaningful. This is characteristic of quantum lipids, so we're interested in it. And the scaling collapse is consistent with proximity and point. And I have enough time, I'll say a bit about that at the end. Okay, so I think I should get out of the way very soon is to say these people were responsible for a lot of all of the best ideas in this work. Sid is a PhD student, graduating soon, and he's our intellectual. You read all the quantum information literature in the original and went deep on those ideas. And Tokoro did a lot of the heavy lifting on the numerics, and it is pretty heavy by the end of the talk. And actually, both of them visited here, I guess, on the occasion.
Yeah.
Anyway, so Elizabeth will recognize this. I was an undergraduate at Birmingham, and this guy was my tutor, and I was thinking about what to do with my life. I decided I was going to do theory rather than experiment. What kind of theory am I going to do? I'm interested in statistical physics. I'm interested in quantum mechanics. Ray was a statistical physicist. And I said I was thinking about doing materials. He said, well, what's so great about H-file? Why don't you do classical statistical physics? And that was actually a really, really good question. And I still think about that from time to time. What is so great about H-file? Why have I spent so much of my life doing this stuff? So what is special about quantum mechanics? Well, some things are different. You have commutation relations that matter when you quantize statements. However, you can do that and still live quite close to classical physics. And as Sergio Roche wisely said, the universe is mostly a semi-classical place. Most of the time, you only need a minimum amount of quantum mechanics to really understand what's going on. So you need this. You need quantum statistics, which actually is the corollary of this. And most of the time, you don't need much else. However, there are exceptions. Quantum computers are not certainly classical. And well, the simplest thing, or the earliest things I know that really distinguishes these cases is entanglement. So, you trace that back, we end up with this very, very famous paper, which addressed the foundations of quantum mechanics and whether it's a complete theory. And that was big news. It's New York Times front page, I think. And the argument in the paper comes down to this. They figured out general relativity, they knew about light cones, they knew that you couldn't influence an event outside the light beam. You've got to send a signal from one place to another to have an effect. So in classical physics, actions taken today have no effect. B is outside the light cone. But Einstein and friends pointed out in quantum physics it's not like that. You could do a measurement here and it could have some consequence here. And that they claimed that was just wrong. So quantum mechanics is not complete. It's something we haven't figured out. It got called spooky action at a distance. Einstein had that fantastic way with words. So the heavyweights weighed in. Bohr writes a paper with, Bohr writes a paper with the same name, saying Einstein's just not got his head around quantum mechanics yet, and it's different. And Schrödinger cut straight to the chase and says, the best possible knowledge of the whole does not include the best possible knowledge of its parts. And that's essentially entanglement defined in a sentence. He originally wrote it in German, but then he kind of followed up in English, and the English version of the paper was the first published use of the word entanglement, but nobody remembers that, except scholars of foundations of quantum mechanics. What everybody remembers is the cat, which is a throwaway one-line remark in that, intended to demonstrate entanglement. It's not particularly intended to torture cats, but that is more the message we'll take away. So, just to complete the history, Bohm did weigh in. We should be grateful because they rephrased Einstein's paradox in terms of spin states, which makes it an awful lot easier for the rest of us to follow what's going on. And Bell and wrote down some very, very famous inequalities which enable you to establish when there is a quantum effect, specifically a quantum effect, giving an entanglement. He also, I think, really closed the debate on whether a local hidden variable theory could ever replace quantum mechanics in co-op. Quantum mechanics is inherently non-local. As Bohr said, live with it. That's just how the theory is. It works pretty well, so I don't think it's so bad having to live with it. But it has consequences. Here's Schrodinger's analogy in Bohm's language. So that's a singlet, or it's an EPR state, or a Bell state, if you're a quantum mechanics. So here's the cat alive. Here's the radioactive ion not decayed. It's the cat dead. Very sad. If the radioactive ion decayed. And this often gets said as the cat is alive and dead at the same time, and that is not at all what Schrödinger was trying to get. What he was trying to get across was that you couldn't extract information about the cat or the radioactive ion. Complete knowledge. You can't write it as things I know about the cat and things I know about the ion. So you can know everything that's possible to know about the wave function of the whole system. You still don't know what the individual bits do. Now that's the fundamentally different thing, quantum mechanics, from classical physics, where you know everything, well, you know everything about the things that make up everything. Quantum mechanics doesn't work like that. So the best possible knowledge of the whole does not include the best possible knowledge of the part. I'm showing to this point. And he named it for Schenkel, which I think means something like weaving or intertwining. It's actually a phonetic word. And his English translation of that, his translation of ours, was entanglement. Okay, so what do you need to know? I'm not desperately philosophical in my take on quantum mechanics. It's a tool I use for my work. It's kind of fun work. But you need to know some stuff. You need to know that if you have a state, which is a superposition of products of states, it's system A, system B, but in general, you won't be able to decompose that into a state of system A times a state of system B. They just won't work. And you have to know. Okay. And this is true for anything. It's not just spins, cats is a bit of a stretch, but anything that provides fluids or quantum mechanics. So it's particularly. What's it good for? You know a lot about that these days. Quantum cryptography, so secrets that are protected against eavesdropping. That would be useful unless you can communicate them in some way, as you can, using entanglement. Quantum computing, you hear a lot about that. I'd like to point out that it wasn't always as fashionable. Richard Joseph was in the University of Plymouth before everybody wanted. So his foundation work was done in a primary teaching institution or a research institution. You see that again, people. And my favourite, quantum spin liquids, things that I hope that will be measured here in a few years' time. So that idea we can trace back to Anderson's article in Cambridge, 1972. And he wrote a paper saying that you can imagine something different from convolutional. So if you have a system which is very frustrated, where the usual semi-classical physics breaks down because of interactions, instead of getting a Néel order parameter, let's say, you could get a state which is a superposition of lots and lots of different single configurations. And you're already going to see from the way I showed you before that that's very entangled. My Russian friends would probably like to point out there's an even earlier paper by Pomeranchuk, but it's even harder to understand than Anderson's original patents. Good luck. Okay, so here's the RVB idea. We intuitively involve a state involving a superposition exponentially large numbers of different single conjugates to be very entangled. And it is very entangled. That intuition is right. Is a anthropomorphic or capomorphic way of explaining it. It's not superposition of alive and dead, it's the superposition of everything a cat could ever do all at the same time. That's what quantum spin liquids like. And they have many, many interesting properties as a result of that. For a long time, hard-nosed experimentalists laughed at us for saying things like this and said, you'll never measure that in experiments, it's got nothing to do with reality. You're like a little child that dreams of unicorns and you should go off and play in your playroom and solve equations. It's got nothing to do with us. Happily, that changed. And in the last 20 years, there have been a great many investigations of quantum liquids, some of them extremely successful. So, that notwithstanding, candidates, particularly two-dimensional candidates, tend to be quite controversial. Here's my favourite two-dimensional quantum spin liquid, helium-3. There are organics. So, but Smithite, this is sort of a Kagame. There's alpha ruthenium trichloride. You could write long books on controversies involving ruthenium trichloride. We showed you the turbulent triangular ladder system. These are kind of cute. And every single one of these is contested. People fight about the interpretive experiments. It's not unambiguously clear that it's a spin liquid, except possibly the helium-3, where there have been no new experiments in the last 20 years that I've noticed. There are only three groups in the world who could ever do the experiments anyway, so I'm hoping somebody will come back to that one. Anyway, so why are they so? And actually, I think the best example of a spin liquid in many ways is the spin-half spin chain, which we understand terribly well, but it's actually mathematically exactly so. So we spin half moments, we let them interact, we put them in a line. You can solve this by beta ansatz. My friend JS has made a wonderful career out of calculating the consequences of this, which is actually quite hard. We can do it. You get spectral functions that look like this. Here's a measurement, I think that maps, which looks exactly like that. You can parameterize this exquisitely. And these are the fractionalized spin-on excitations. This does not have spin waves. You excite one spin, a neutron, and immediately the energy transfers into 2, 4, 6, 8, 10, 12 spin-on excitations. I think JS's calculations go up to about 10 or 12, at which point the hierarchy, it gets so weak, you don't worry about the others. Very different from this relatively well understood, also important magnet. But this is kind of what spin liquids are like in 2D or 3D. It's difficult because you can't just look at it and interpret it, and you can this. So no individual quasi-particle excitations that couple directly to neutrons. And also, they tend to have structured diffuse scattering. Here was a spin liquid candidate, faceted in zirconate, pyroxyle, 3D this time. So this is an interesting structure here. Part of the reason they thought this might be a quantum spin liquid was it looked a lot like our predictions for a certain type of quantum spin liquid, which we also understand quite well theoretically. But I think now the accepted interpretation is this is quadripolar order, which has some disorder contribution to it as well. The point is, just looking at this pretty picture, and this picture, there's not so much to choose between them. Which does it look more like? This one or this one? Play with the color schemes a bit, play with the parameters a bit. It's not really decisive. And that problem comes back again and again and again. You have diffuse structure, you're not looking at bragg peaks, you're looking at spectral waves, just spread out in similar space. It's very hard to say then what it is. So, how can we tell quantum spin liquid-like correlations come well, sort of quantum spin liquid correlations come from fluctuations? And this is where we need to go back to those foundational ideas of quantum mechanics. What makes quantum fluctuations different? So, modern papers on quantum spin liquids routinely invoke entanglement. Here's a review that says, well, nobody can agree about what spin liquids are, but we're going to say they're very entangled. That's true. Actually, it turns out quantum Rydbergs pretty entangled too. That's another story. Here's us at the same game. Quantum entangled. We're not wrong. You have to go an awful lot deeper to really understand what that means. How many spins can we entangle? This is kind of amusing. If you buy the praseodymium hafnate, is an example of a quantum spin ice. We have an estimate of the speed of light. That is about 4-hour marathon pace. That's how fast the photons go. We can turn this into a thermal de Broglie wavelength, which tells you roughly the volume over which spins are correlated. And each spin is then entangled with about 1 million other spins at 50 milli-K. This is considerably better than quantum computer. They've gone up to about 1,000 qubits now, but they certainly can't entangle 1 million. So if you're a quantum materials person, you can take some pride in the fact that we are many orders of magnitude ahead of quantum computing in terms of the degree of entanglement that we can accomplish without even trying that hard. We cooled this down to 10 milli-K, which take a bit of patience, but could be done, and you'd be entangling 10 to the 8 spins, according to this back of the envelope calculation, which is incidentally almost certainly not an overestimate, not an overestimate. That's kind of fun. Okay, now we need to get a bit more mathematical. We've got to start quantifying the entanglement more seriously than my back of the envelope estimate. Here's the first tool we'd go to. Von Neumann, one of the great minds, another of the great minds of the last century, was interested in the connection between quantum mechanics and entropy, because you've got to get entropy right if you're ever going to explain classical physics. And he worked out you could write this as a trace over the density matrix. We now write that as rho log rho. It's the same thing in German. And we can go a step further, trace out half of the density matrix, bipartition our system, and then look at the entanglement entropy associated with this bipartition. And if that's finite, that is a measure of the information involved in separating the system. So it's a numerical count of what Schrödinger was trying to tell us about the stuff we don't know. When we look at only half of the system, we've lost knowledge. So this is a very useful measure theoretically. I want to show you that it can answer the question that we set up, but it's not going to be a practical experiment. So we take our spin chain, or put some disorder in, or disorder on the bonds. Then it turns out not to matter exactly how you put the disorder in very much. So we'll do what's easy. In the absence of disorder, it's the spin liquid we already saw, and the entanglement entropy calculated with this solution diverges with the size of the system that's logarithmically divergent. Now, if we put disorder in, we get a random singlet phase, which is composed of singlets that are length scales. And you might think there's so much long-range entanglement in that, but there is. In fact, what happens is just that you get a renormalization of this coefficient. Still diverges logarithmically. And if you know about high energy physics, the ADF-CFT conjecture, that's actually the first place where this logarithmic divergence is calculated, and it's ubiquitous. You do a linear spin wave estimate of entanglement entropy, Lund and Cooper, you'll see no divergence. So this is quite common. However, we've got pretty good at calculating these numerically, and we can calculate for disorder-free and disordered, and you can see the difference in coefficient. So in principle, you could use this to distinguish the disorder phase and the spin liquid phase. In principle, there's a very obvious problem, which is you just can't measure it. The caveat to that is cold atom, because they can make many, many copies of the same state reliably. They can make copies of state that interfere them with each other. And in that way, they can painstakingly reproduce at least an estimate of the entanglement entropy. So this is a kind of tour de force thing you can do with relatively small numbers of particles, manipulated as cold atoms. This is not going to work for the systems that we're interested in. So does that mean that this is not going to work for us, even when we finish building this big, beautiful instrument here? We won't be able to measure the entanglement entropy with it. That's just quantum information, not a useful thing to think about. Well, happily, information is still a useful thing to think about. There's other ways of getting at this information. But to see that, we need to go a bit deeper into the quantum information toolbox, not just stop at entanglement entropy. How else can we look for it? This is relatively recent science. In the 1990s, some information community who frankly didn't care about neutron scattering or materials or anything like that, wanted to solve the question in principle. How would they know whether entanglement there? What were the necessary conditions? So these three brothers from Gdansk wrote a paper on separability of mixed states, which is basically can a mixed state be entangled? How do I know that? Mixed states, basically quantum mechanics at finite temperature for us. That's what that means. And everything we do is at finite temperature, everything we care about. So we need to care about this. Barbara Tahal followed up, going back to the Bell inequalities and saying, okay, anything that violates the Bell inequality can be used as a witness of entanglement, so a test whether the knowledge there. And this is going to work for mixed states, building on what they say. So if you want to read up on the nitty-gritty of this, there's a review article by these people. Actually, there's also a review article by these people. Many objects can act as entanglement witnesses. This is some of the good news. So because quantum mechanics affects everything, in fact, the entanglement corrections start to creep into a lot of stuff that you're measuring anyway. So this is a review aimed more at our community, witnessing entanglement. And here you'll see listed various entanglement witnesses, so things which are in principle tests of entanglement. And you know them, well, you know some of them. Magnetic susceptibility, equal time structure factor, equal time structure factor, interpreted suitably, etc., etc. So this stuff's not so weird after all. It's already being measured, all the information is already in principle then expanded. It's just not being interpreted in the way that you would need to extract the quantum ideas. And in fact, Alan Shea's written a kind of review article of the review article of the review article specifically aimed at neutron scattering people who don't want to maybe read all of the original quantum information papers. I'm grateful to Sid that he did. Okay, let's start with two spins. That's easier. Here's a paper by somebody else from a teaching institution, William Wooters. And we consider just a pair of spins, or two qubits. And we consider how much entanglement you need to generate an arbitrary state of two spins. This is a way of measuring entanglement. It's also something called entanglement distillation, because how much you can get back out. It's completely obvious they're the same thing, but we don't need to worry about that level of distinction at this point. So we can quantify it for something called concurrence, which looks weird. All I really want you to take away from this is that there's a max there. So we compare 0 with some strange combination of the eigenvalues of some matrix, which we'll construct like this. We take the density matrix, we do time reversal on it with these Pauli operations, we multiply it by its not time reversed version, and then we diagonalize that to get its eigenvalues, and we compare them with 0, difference of 0. And we take the biggest, 0 or that. Okay? And that, believe it or not, and you can derive this in a few pages, it's not a very long derivation, measures the entanglement formation, and therefore the amount of entanglement is there. By definition, this is going to work out between 0, which is the lowest value you can get, and in fact 1, which is what you get for a Bell state similar. So just to spell that out, if you see a value that's not 0, found entanglement, you can quantify it. 0 is product state, something between 0 and 1, 1. Now, the nice thing about this is because it was derived from mixed state, you can apply it to two spins in the hull. So you can have something.
Sorry, can I just ask you a
Yeah,
question?
sure.
What does it mean, entanglement monotone?
It means it gets monotonically bigger as the entanglement gets bigger.
Okay.
So therefore you can use it to measure the amount of entanglement. And it is basically.
Okay. Sorry for interrupting.
No, I'm very willing to take questions. And then when the time runs out, you can decide whether you want me to carry on talking or not. But please feel free to interrupt if you want to. I'm treating this as a fairly relaxed occasion. I hope that's appropriate. Okay, so we can use this as a measure. And because it's been defined from the density matrix, it works for experiment. It works at finite temperature. It works for the out of two spins in a much bigger ensemble. And I should call it a reduced density matrix of measures. It works, basically. So why is this a big deal? You know how to measure spin correlations. You know than me how to measure spin correlations. There's enough information there, in principle, to reconstruct the reduced density matrix with the spins. From that, you can, in principle, construct that. Let's restrict ourselves to things that least the U1 symmetry. It looks a bit easier then. We write it down in terms of equal times functions like that. That doesn't look so intimidating now. Just slightly ugly. It's not that bad, right? So, in return for substantial investment in a nice instrument, you can measure the dynamical structure factor, and from that you can extract concurrence. Sounds good. So, it doesn't stop there. This is a measure of entangle 2 spins, but you could also entangle 3 spins, or 4, or 5, or 6, or an infinite number of spins. I was already joking about how many orders of magnitude we are ahead of quantum computing. So we also
in a non-controlled way. So in other words, you cannot use it. With the way you create your thing, you cannot use it directly for it.
That's the thing you've done with that.
yeah, okay, so
Not yet.
we could have a very long side discussion about this. I will just say one or two things. In the sense of circuit-based quantum computation, no, which is a totally different paradigm. However, assuming you know about the surface code, which is the way of building a fault-tolerant circuit-based computer, okay. So the way that they're all trying to do error correction in quantum computing is an idea taken directly from quantum spin limits. So in fact, if you can get a quantum computer to work, it's essentially by simulating a particular time. That's a very short version of the answer. And what we'll be able to do with our entanglement long term, I will run what Pascal's. We don't know yet.
No, that's a good. I totally accept that we don't know yet. I'm totally happy with that.
But the circuit-based paradigm is very interesting. A lot of really fun stuff happening with that. When people simulating quantum liquids on quantum computers, circuit-based ones, essentially trying to do error correction, but they kind of have to do spin liquids along the way because that's what they're having error correction with. That's a different subject from what can you measure here, which is what I'm really into. So there are lots and lots of other measures of entanglement. A lot of very smart people thought about this stuff in the 90s and wrote down different ways of doing it. I'm going to mention just one more, which will turn out to be the one that we care most about. So this is Fisher, somewhat fascist in his views on many things, but the founder of modern statistics. We'll run with that. And one of his major contributions was to write down a way of calculating how much information a variable x contains about parameter theta. And that's the kind of thing you'd often want to know. Given the probability distribution, you can calculate this. Now you can do it with quantum mechanics, instead with your probability distribution, you really need to work with the density matrix. Now we can do exponential, the density matrix and do anything. So here's a density matrix. It's going to be some convex sum matrix elements like this. By convex, this means these things positive, so they can be interpreted as probability distribution. And here's quantum Fisher information expressed in terms of matrix elements as an operator. It said what the operator is. Then we didn't say what this variable was either. It's whatever it needs to be. And the cute bit is, since it can be whatever it needs to be, it can be something you can measure with a neutron. So a Fourier transform of the spin. Here I put uniform magnetization, but could be at some Q. And then there's a subject to certain assumptions on the boundedness of this operator, which I'm not going to go into. We end up with a very direct interpretation in terms of a bound on the depth of entanglement. So if this is bigger than some integer, then it tells that your state is at least k plus 1 parts entangled. So if it's bigger than 2, you've entangled at least 3 spins. It's bigger than 3, you've entangled at least 4 spins. Right? That probably sounds weird, but there's some rigorous mathematics behind this. As long as you make your operator satisfies some relatively benign conditions. Okay, so in a thermal state, it's a relatively recent paper by Peter Zoller and others. They calculated this and pointed out, hey, look, I've got this operator in here for your transform of spin components. What I'm measuring is really some integral thermal factor in naturally inverted dynamic susceptibility. You can measure this. You measure this lots of different ways. So that is a practical working tool. Good. So, in return for your 3 million, a lot of hard work, you can measure the number of structure factors from these. You in principle get concurrence and get Fisher information. Okay? Quantify 2-spin entanglement, find if any part of entanglement is present. How well does this work out? So let's go back to Allen, their study of this spin chain, potassium copper fluoride, maps, DMIG, green. We understand this very well. We can calculate concurrence and equal time correlations. This is SC correlations. Essentially, get about it 2 tangle, which is the sum of all the concurrences, so that we don't have to keep track of all of the different bonds. Calculate this as a function of temperature. Use the same parameters that agreed so beautifully with the experiment here. It's not beautiful. Experimental results do not have simulations. Something's going wrong. If we look at the quantum Fisher information, however, everything agrees very nicely. Okay, so there's something that hasn't really worked out with concurrence. Quantum Fisher is still standing. There's maps. I think this was built using spare change they found down the back of the safe, spare parts that they found lying around somewhere else. But it's still a pretty good instrument. And they were able to get concurrence on the Fisher information. This one, it's got a question mark. This would be. Where do they go next? Yeah. So with their equivalent instrument, they measured this triangular lattice antiferromagnet. So we've got a terbium spin half, sort of spin half on a triangular lattice. It's actually a now ordered system, well, moderate moment, not very small. The minimal model that they advocate is the J1, J2 Heisenberg model, so something computing secondary rooms. And we'll run with that, though I'm slightly skeptical about describing the terbium 3+ in terms of the Heisenberg model. It's usually anisotropic. They claim it isn't here. Here's correlation to the ordering vector. Here's the dynamical structure factor at the ordering vector. You can see there's some continuum. It doesn't, to be fair, look so much like conventional spin models. So while it might have now order, it's not something you'd look at it and just say, oh, that's the spin rate, the gold standard. But if you've got this information, we can calculate QFI and concurrence. So they did that. We'll concentrate on the QFI, related to dynamical susceptibility like this. They've only got 3 temperatures, but I don't need to say why. Each of these is a time-consuming experiment. And they have taken these numbers very seriously. Okay? So they've said, because here's 2-particle entanglement, which is QFI greater than 1, here's 3-particle, which is QFI greater than 2. Because below this temperature, we have more than 2 spins entangled, it can't be a random singular phase. It can't be disorder physics that's making it very strange. Okay. So that's their claim. It's assumed to rule out disorder in random singles then. That behavior, I failed to emphasize something important there, which is that they plotted this on a linear scale, but if you plot that on a log-log scale, Yeah, pretty straight line. So I'm not going to talk about how people use NUSR to estimate quantum Fisher information, because I think this is very promising, but there's also a little bit of work to do to maybe tie down the matrix elements. But here, they do plot on a log-log scale, and you see a little straight line. This is another triangular lattice, antiferromagnet, quantum spin liquid candor. This is a triangular lattice, antiferromagnet, quantum spin, and straight line, parallel. Okay. And here all three plotted on the same axes, and it's more or less the same parallel. And the difference between this and this, well, yeah, what exactly the matrix element is, so it's a little bit ambiguous to me at least, which I think means there's plausibly a constant factor between the estimates anyway.
For the inelastic neutron data, it seems to me that you have to subtract off the background in a very careful
It'd
way.
be even better if there was no background.
But is there,
Yeah, you're absolutely right.
because that will have.
Please build instruments with very low background.
We should speak to Pascal.
We're on it.
Yeah, you're absolutely right. And it's worse than that because you're integrating over all frequencies, which means you're getting up to where the phonons start to contribute as well. So it's quite a lot of things.
Because in their paper, it says they're looking at the sort of around the third correlations.
Mm-hmm.
So they must integrate a small region in Q. I don't think
It's the omega you worry about.
Yeah,
Is
so
that integral goes to
you're
infinity.
integrating all of energy,
Yeah.
absolutely, but you're integrating in Q quite a small region.
Yeah, ideally one wave vector. Though of course in an experiment you always got some.
Yeah, plus and minus, okay.
Yeah.
That's
So your one vector is the operator you chose to put in the quantum Fisher information, and that's a choice. And then you need to integrate that over all frequencies, multiplied by this thermal factor. And what that thermal factor does is basically to squash the low frequency stuff. With the high frequency stuff you need to worry about. And the higher you go in frequency, the more sources of noise, whatever the low frequencies, the annoying elastic line, and those things tend to get squashed by the thermal factor. So that's less of an issue. And happily for us in calculations, we have issues at low frequencies and finite size effect, and they also get squashed by that thermal factor. So.
But I've never seen a Q does the Q dependence across?
Nobody's
Q?
measured it.
But they have measured, but they just haven't extracted it. Clearly
Okay, they haven't extracted it yet, so.
So
I mean, it would be probably much cheaper for us to do this in simulation. But it hasn't been investigated. So it's an interesting question. Well, I'm inferring the question here, but I don't think it's investigated.
yeah, that's interesting.
But it's going to be an awful lot cheaper to check that out in simulation. Not another experiment.
But we've already run lots of these.
Oh, true. You can do that.
Bella has a question.
Well, hello, Bella. I'm not managing the meeting, so somebody else will need to. Somebody else will need to let Bella
Hello?
speak.
Hello?
Yep.
You here?
Yeah, can you hear me?
Yes, yes, yeah. I just wanted to say that when you go away from the Q equals pi, then you get a smaller value of the quantum Fisher information. So
Yeah,
it's largest at the sort of gapless point.
that's right. Yeah.
So that's
and
why they's always been chosen to be done there.
Yes. Though I'm going to argue that what's interesting is the temperature dependence, not the number.
Yes. It's just that I suppose I'm just saying that was the reason why people focus on that point, because they get the highest number there.
That's right. That is a very good, and they wanted to establish that they wanted to get the biggest bound on depth of entanglement they could.
Yeah.
And then you're quite right. You'd sit at the ordering very factor.
Anyway, sorry to interrupt. I'll go away now. I'll go now.
No, thank you, Bella. I have a stupid question with that. So we say that we have a sort of entangled state that from your numbers extend over 240 angstrom with 10 to the 6 spins.
That was my cheeky back there.
Yeah, no, and I like it. I like it a lot.
Yeah.
But surely, why I have this image, which is maybe too classical, of it being completely entangled, so it shouldn't really matter where you are in Q.
Yeah, so that touches on a lot of very interesting things
Yes.
that I haven't put in the talk because it's going to be too long anyway. So for Preston Mahaffinate, I mean, the thing you start from the pinch points, right?
Yeah.
Temperature dependent on the pinch points is the thing you use to estimate speed of light. And that's what my thermometric wavelength is. So the ground state, everything is entangled with everything. But the signal of everything being entangled with everything is spread out over all of receptacle space. And this quantum Fisher information idea is not going to be desperately useful there because the major elements that you can measure, the operators that you can measure, the neutron scattering, are not coupling very directly to things that you've been entangled. Things that you've been entangled. Spin ice and fluctuation one of care. So that's much harder to measure. If you had a probe that coupled to those, you'd see some sharp response, like you see now wave vector here that you could do something with. And part of my message at the end is going to be that you really need to pick your fight. That there are some systems, and the triangular lattice antiferrometers are one of them, where this is actually really quite a useful thing to do. And there are others, like my beloved quantum spin ice, where it's actually not so useful, sadly. Kagame, well, we're still working on it, but the naive application of these ideas doesn't work out great for the same reason. You don't have one sharp wave vector to get strong responses. Right.
So could you imagine a situation in which concurrence gives you, say, non-zero only in finite regions, and then the QFI would give you entanglement across the sample?
Can I come back to that question a bit later? Because I have some more things to say about concurrence, and there's some more surprises. Or at least there were surprises to me. Maybe everybody else will see it come. Okay, so there's something else here which is very cute. I'm not sure this is very relevant, but it's too pretty not to show. So Alan spotted that if he took his data, multiplied it by t to the alpha, is his best case alpha, and plotted it as a function of omega upon t, it will collapse into a single curve. So that's a rather nice thing. And they interpret that as evidence that this thing is quite close to a quantum critical point, which is separating the Néel phase. So there's a lot of things that can be said about this phase diagram and the theoretical work of that, and I'm not going to talk about it. I will come back to this if you haven't lost patience with me by then. I want to say some more things about entanglement. What do we need to understand? We need to tie this up. We need to know why two tangles not agreeing. And it's not that the calculations are not well parameterized or not well carried out. That we know how to do things just spin checks. Is it safe to rule out random singlet phases with grounds and multiply entanglement, as they did? How should we interpret this power law? Looks like we're on something here because power law, roughly the same power law, is showing up in lots of these different systems. If we have time, patience, things come back to the scaling collapse. Okay, this one first. So, what happens to concurrence in the presence of disorder? This wasn't something that the people doing foundations of quantum mechanics had to worry about so much, but it is something we have to worry about when all of these materials have disorder. So we can put disorder into the calculations as well. We can do that, calculate concurrence with disordered spin chain. And here are some plots to give you a sense of what's going on. Here's the spin liquid. So I'm relaxing to liquid, the delta was 0, and the concurrence is 0. And that's what really deeply entangled things look like. But there's a property called entanglement monogamy, which means that one spin's only got so much entanglement to give out. And if it's busy being entangled with everything else, it can't share it with another spin. So that's maybe the first surprise, it's just 0. In contrast, if we look in the disordered case, we have some bonds which have really quite high entanglement. These singlets, or random singlet fibers. So that's good, right? This is a really sensitive probe with a delta between them. Except that it isn't. It's a problem. And the problem has to do with how you measure averages over disordered experiment and you calculate. So here you have this max that I drew your attention to, max of 0 and this. And this max is sensitive to whether you do the disorder average before taking the max or after taking the max. If you're doing theory, you take it afterwards, then you get these nice results that I've already shown you. If you're doing experiment, you don't get to do that. You don't average over different samples. You have one very big sample and you average over all the different bits of disorder and the different bits of the sample. So you need to put the average inside here. And by the time you've got a mod sign and a max function, these are totally different results. And this is fatal, actually, for concurrences in experimental measure access this way. Systematic differences to this kind of feature. And the qualitative distinction I showed you in these 3 pictures between quantum liquid and gone. Bad news. That is the end of the road for concurrence, as so far as we're concerned in these things. It's a nice thing to calculate theoretically, but you're measuring in a disordered sample, you get this problem. Okay, so it's an unreliable witness. Bad news. Let's move on to unofficial information. So they've used it very quantitatively. Here, you work hard, you put everything in absolute units. In principle, you can be quantitative. You can say, here's my bound on depth of entanglement. It's clearly bigger than 2. Singlet's 2, so random single states out of the question, right? Well, it turns out there's some subtleties here too. So here's the QFI for a finite size system as a functional wave vector. You see the peak at I. If you do finite size scaling, because of course we can't calculate from Avogadro number of spins, you see that in the spin liquid, it's scaling towards infinity, and in the random singlet state, it isn't. It seems to be scaling to a number. We can't say definitively what that number is. It's already bigger than 1. So this tells you that the random singlet phase also shares multiple time. Okay. If we look closely at this, what we realize is that up to some length scale, you really can't tell it apart. Only do it by from liquid. And so up to that length scale, it's doing the same things. So liquid is according to this measure. And if we run with that, about this crossover scale, we can make an upgrade to a cartoon and say that, well, each of these points here, this is an effective spin half, built of some number of spins, act together, and therefore there's a finite depth entanglement. So there's a theory that I'm not telling you about called the strongest order renormalization group, which this cartoon is associated with. And if you go back to the original paper, random antiferrate from the spin chains, there's actually a quite original paper, but it's the one that everybody reads. Here's the cartoon. This is the thing that people take away from the paper. If you read the small print, which people tend not to do, oops, the small print says the spin half objects that make up the lowest units spread out over a number of lattice sets. So in fact, the finite depth of entanglement was always built into this picture. They just don't. People look at the cartoon and read the words that go on. Right? So they need to be surprised, but it's not as simple as that to rule out these disordered players. You need to think more carefully about what's going on in competition. And in a way, this is, I think, liberating. Numbers and matter so much. How things change matter. Temperatures are the thing we've investigated, Pascal's plugging this about wave vector, and then you have things. Okay, so was it safe to rule out the random singlet phase? No, it wasn't. It was an understandable mistake. No, it wasn't. All right. Okay. Now let's look at something that seems robust and interesting. So how should we interpret this? So now we need to generalize our model with disorders of triangular lattice. So this is the same thing. We take this J1, J2 Heisenberg model, we put the disorder in the same we did with the 1D spin chain. Here's the zero disorder line, spin liquid, NAL, stroke phase, those end up to some finite value of disorder, and then we have something here it's called spin liquid like phase. I'm going to call it a random singlet phase as a kind of flag of convenience, really. There's a universally agreed name for this. And if you look in the correlations of this, it's been pretty well investigated by Karamura's group, going back about 10, 15 years. And it has some quite interesting properties. You can see the fluctuations are mostly at the zone corner again. There's some quasi-continued excitations. Heat capacity is linear. That is not often the surface. That's just a lot of states very close together in energy. If you go to real space pictures and simulations, you do find singlets. You also find some orphan spins. There's consequences for the susceptibility. So can we distinguish these phases? Well, let's have a go. Here's our simplified version of that cartoon phase, of that phase diagram, schematic, random singlet, common spin liquid down here, and stripe. And we'll pick some representative parameters. That's the pure Heisenberg model, no further interactions, no disorder. That's a deployment spin liquid, due to J2, again, no disorder. This is the point that Karamura studied, Heisenberg modeled quite strong disorder. And well, unless you're very sensitive to colors, it's the same, right? Correlations don't look qualitatively different at all. So now column spin liquid and random singlet phases in this model is really poorly differentiated by S and Q. So it's both bad news and good news. It's bad news in as much as that you can't just look at your results and you sort of scatter and say, I know what that is. There's good news in as much as, coming back to Bella's point, there's quite a lot of spectral weight lying around at that ordering vector in each of these cases, and you can do something. So what does concurrence tell us? Well, I told you not to believe concurrence, but I'll show you again what to believe it. So here's the random singlet phase. It's very pretty, actually. This is simulation. This is not implanting. These are the results for one particular disorder visualization. Here's singlets. Quantum spin liquid, again, because the entanglement's been spread out among all of the spins, you see nothing on the individual bonds, that is zero. That looks like a beautiful signature distinguishing them. Until you put the disorder in, and you think about the order of averages, then it all goes horribly wrong, just like it did in the 1D case. In fact, more horribly wrong. So we're going to give up concurrence. Maybe theoretically it's interesting to talk about. Experimentally, once you take care of that, it's just not useful. Dead end. For details, see Sid's paper. What about the multiple entanglement? So this is the thing that we're going to advocate, as witnessed by quantum Fisher information. Strongest fluctuations with K equals Q, so we're valuing Q via this wave vector. This is what we find. It's not totally cheap for us to do these calculations. These involve the largest supercomputer in Japan, working moderately hard. We have to do dynamics at finite temperature. Quantum dynamics, that's not easy, but I'm not going to talk about that side of it. What I want to draw your attention to is that we have two qualitatively different behaviors going on here. So the random singlet phase, the red points, seem to start at a number and just decay, whereas the NAL and the quantum spin liquid, if we ignore the smaller system, that triangle there, still going up. Get down to low temperatures. We can't go down to super low temperatures reliably because of finite size of things. You can go up really high in temperature, and that's fine. This is what we find for QFI at this wave vector in simulation. So clearly all of these phases are entangled. At this point, you shouldn't be surprised about that. Essentially everything, if you made it cold enough, was acids and scaling, it's like we might distinguish them. So now let's take the same data, plot it in two different ways. So we'll plot the NAL and quantum spin liquid on a log-log scale, and that's a tolerably good straight line. So we can interpret this as a power law. And we'll plot this on a log linear scale, and that's a very good straight line. So that's exponential. So don't worry about the numbers so much, the qualitative behavior, and it's very distinguishing. The numbers not so much. Everything has got some finite depth independent, but the way it gets there or the way it loses it to heat it up, that's really quite different. So, how does this compare with the experiment? So we'll take the parameters that Alan and friends tell us we should take, this ratio of J2 upon J1. J1's about 6, I think. I'll put that on the slide. Here's simulation for those parameters. We've done quite a wide range of temperatures. We have finite size effects we worry about low temperature. They don't have to worry about finite size effects. Obviously, there are experimental limitations in temperatures. So these are both tolerably good straight lines and behaviors over the range that we've plotted. This is taken from simulation. This is taken from experiment. We have some finite size effects in our dynamical structure factor and energy. But happily, when we calculate QFI, these get squashed by the thermal factors. Don't worry about that size effects as much as we might otherwise. Most of the contributions come in as high frequencies. Okay, so we find a similar power law scaling to experiment with a higher absolute value of QFI. And remember, we didn't put the disorder in this calculation of the real systems. So I'm pretty sure that by allowing yourself a few more parameters, you could close the gap between. Okay, MuSR was really intriguing. Here's our calculations for their parameterization. We find basically the same slope as them. Again, there's a difference in absolute values, but again, it's disorder first, and it's missing modeling. And I am still not sure if I understand what that MuSR matrix element is. Same thing for this. Our law, pretty much the same slope in simulation as well. So this looks good. So the simulations of both of these columns with good candidates reproduce power law scaling, similar experiment, higher absolute value. Don't worry about the absolute value, that's sensitive to lots of things. Worry about how it's changed in temperature. So how should we interpret the power law? It's characteristic of both the quantum spin liquid on the air basis. Now, if you need to tell quantum spin liquid nail, that's not so hard. Is there a breakthrough? Yes, it's a nail phase. No, it's not a nail phase. So that we won't worry about. This is distinguishing from the random singular phase, which is a thing we wanted to use. Okay, if you're still interested, I will tell you a few brief things about the scaling. So I'm conscious I'm over time. But if you're still listening, I will keep going. So does simulation also find a scaling collapse? You can probably guess that it does, or I wouldn't keep going. Here's Alan's interpretation of the experiment. Here's Tokaro's heavyweight numerics. And here's the scaling collapse for the same experiment. We can actually get a slightly better scaling collapse using a slightly larger experiment. And we're digging around in the theory literature at the moment, trying to work out what the experiment should be according to RG calculations. That it's not so clear, it's no. But a number may be approaching 2. And if we plot both together, no adjustable parameters, yeah, so nice. You can see that the experiment and theory agree quite nicely over many orders of magnitude. This reminds level. So we're proud of that. It ain't perfect agreement quantitatively, but that's as good as I think you should ever expect, given the approximations that you made. Okay, so that's nice. What does it mean? Well, have we seen this kind of thing before? Yes. And those of you who are of my age will remember the craze for quantum critical points, which has maybe never entirely gone away. And this kind of scaling behavior is the hallmark of the quantum critical point, or we normalize classical physics near to it. This was studied by Andre, who worked with Once Upon a Time in Sevilla, and they produced scaling forms that measured in their value of exponent. This is a large N estimate, is a little different in an experiment, but I think I won't worry about that too much. Inference But this system is close to a quantum critical point, but specifically the quantum critical point associated with quantum liquids seems reasonable. Okay, so what have we learned? We've learned not to trust concurrence in the presence of disorder. Sorry about that. It's just how it is. We've learned that everything has some finite depth at entanglement at low temperatures and can't rule out singular phases from the quantum Fisher information number value alone. Temperature dependence, on the other hand, seems to be quite distinguishing. And this power law behavior is observed in a range of these triangular lattice materials. So that's a good thing to focus on. We can also explain this scaling collapse. It seems to be consistent with proximity to quantum critical point. Where does this leave us? So where might the quantum information approach be useful? So you really want to distinguish phases with qualitatively similar equal time correlations, but qualitatively different entanglement properties. And this is going to be a working strategy where these qualitatively similar equal time correlations involve some at least one point in reciprocal space that you can focus on the neutron scattering and see a meaningful change so function of temperature. So like the train has there. So tools taken from quantum information, at least in the case I showed you, can distinguish. Here, power law, here exponential decay. So apples and oranges. Qualitatively different temperature dependence of this band bone entanglement. What do we need to make this work? Well, you, or some of you. This is a very bright source of neutrons. That's very good because it means the business of measuring temperature dependence is less painful than it might be if you have a less intense source of neutrons. You get them more quickly at higher temperatures. And you need some really nice instruments, preferably with very low background, that you can, and bridges that enable you to withstand low temperatures. Excellent, well-motivated people to run such equipment, get it all to work. And I'm looking forward to coming back here in a few years' time and seeing where it all goes. So thank you for listening. The 1D results are very recently published, the 2D stuff on the preprint server. And if you are curious about our visiting program, I love that. You're in charge, Pascal.
Okay, well, I mean, really, from my perspective, that's wonderful. It has cleared up quite a few things for me, actually. So thank you very much. Do we have any questions?
There are questions online from Bella.
Okay.
Ella?
Hello again, Bella.
Sorry, I didn't have a question ready. Well, I was doing the clap hands, I thought. Actually, I do have a question. So finally, in the end, did you show that there is scaling in the case of the triangular magnet if there's no randomness? And if there is randomness, I didn't then finally get what the difference is. It doesn't scale or it scales differently?
It scales differently. Yeah. So this is probably the most relevant slide. Here is power law behavior. This is found in both the nail phase and the quantum spin liquid.
Yes.
Here is exponential decay. That's fairly strong coupling randomness. You're allowed to ask, okay, what happens if we play with the value of the randomness and tune it? Well, maybe my experimental system is not that random, but it's going to be a bit random. And that stuff we're investigating, but it costs rather a lot of supercomputer time to do the disorder calculation. So I'll have to get back to you with the answers. But we are thinking about that. So at least for these cases, It's very, very clear distinction. And I'm very encouraged that the power law behavior really looks a lot like what's seen in both the potassium and terbium selenide and SAR measurements of these other systems. So I think the power law has a meaning.
So-
the exponential decay.
okay.
Yeah.
For the triangular system, the parallel behavior you state as T over J1.
J1's a flag of convenience. If I was in full theorist mode, I'd probably write a spin stiffness.
Right,
It's just
okay,
a
so
relevant
it's not
energy scale.
necessarily relevant, it's simply the
It's just-
exponential
yeah.
or the parallel.
Well, I just want to make it dimensionless.
Yeah.
I need to divide it by something which has the same units as KBT in order to have a dimensionless measure, and then I can put an exponent on it. Otherwise, my dimensions change with temperature, and that makes me feel uncomfortable.
No, that's fair enough. Okay. Do we have Claudio?
Is there an explicit, I mean, it is sort of the two questions in one, or sort of, two confusions in one, from my side. Is there a relationship to dimensionality here?
Oh,
If I can conclude my question, so to speak, because of course, I'm seeing the role of disorder, no? But in 1D, if we go back to the original paper by Anderson, everything is super localized, no? It's around the diffusion, random media, blah, blah, blah. Damage. Okay, so there is this aspect which maybe didn't come up explicit to me in what you
I
said.
didn't say anything about it. It's of course true. So disorder is a singular perturbation in 1D.
Right.
So that random singlet phase I was talking about, that occurs for arbitrarily weak disorder.
Exactly.
And here, if you believe our cartoon phase diagram, we're saying that in this two-dimensional system, we need a finite strength of disorder in it into the disorder dominated.
But could this also perhaps alter the way you just disregard in your second slide? Should we trust basically quantification information in presence of disorder, etc.?
The concurrence I don't trust. QFI I like.
Yes, no, right. But maybe there was a point in which you made. So disorder in 2D does give you basically different effects on this spin singlet formation, other than
So the thing I can say most robustly, the thing I've already said, that according to best current estimates, you need a finite disorder.
Okay.
2D, 1D you don't. Now, to be a bit more technical, in 1D, within some range of assumptions about the type of disorder, well, they're not very restrictive, and other interactions, but it's not terribly restrictive. There's a single well-posed fixed point. So there's something called the strong disorder renormalization group, which flows very nicely to a well-defined fixed point, and there's enough numerical summation work to make me at least believe that that's a solved problem. 2D is not a solved problem. People have tried applying SDRG, but it's not so clear that it solves the whole problem in 2 dimensions, and there may be multiple fixed points. I'm more on the side of numerical simulation myself. I've simulated some of these things. We cannot unambiguously say this is this fixed point or this is that fixed point. So it's possible that this random singlet phase deserves to be subdivided in some way, but I'm telling you about because I don't know how to. What we're looking for are robust features of the stuff that we care about. Quantum spin liquid, power laws which distinguish it from that random singlet phase. We think the disorder probably is a singular perturbation here because the quantum spin liquid, we're interpreting it as gaps. That's mildly controversial, but it's either gap or syllabus. At the level of accuracy of that phase diagram, we're not worried about that.
Okay. And again, sorry, Pascal, just
No,
one more, then
please.
stop. And then basically when it comes down to your way to do the disorder average,
Mhm.
I mean, is there, I mean, essentially, say, you didn't specify there. Are you thinking in terms of arithmetical or geometrical? Because there is a difference there again.
I will go back to the slide with the simple 1D stuff. So
Because experimental to me seems more like an arithmetic average, but theoretically maybe that your geometric.
Well, theoretically, you can do either order.
Yeah, exactly, yes.
And we
yes.
did, right?
Uh-huh.
Here is our simulation of the experimental
Right,
averages. Here is what you would naturally do as a theorist, which is you calculate for one realization disorder.
Yeah.
And you calculate for another realization disorder drawn from the ensemble.
Yeah.
You're allowed to ask, how did you define the ensemble? But okay, fine. So it's the same ensemble either way.
Of course.
And you can see the answers just don't look the same. And actually, though it's hard to read, what's really fatal with this difference here between this small number and zero. It's just not working.
Okay.
And that isn't surprising. Once you looked at these equations, you think, well, no, it's not going to, is it? Because these things are fluctuating in sign. There's a max of a zero in something, or just not going around. So, so we discovered this empirically and spent a few days worrying about.
No, because theoretically you can do both. Experimentally, you're bound only to one.
You're here.
Exactly. That's
You
what
can never do
exactly. Yes. But
cold atoms, arguably,
mm.
but our kind of experiment on materials, no, you're always doing that.
Yeah.
And this is the one where it doesn't tell you the things you want to do.
Yeah.
So theoretically, sure, do this and you'll learn something. Experimentally, you can only do this and you won't learn anything. Or at least not the things you think you learn.
Yeah.
Thank you.
Okay. Any further questions, Elizabeth?
So if I think about quantum states with no classical analogues, you already mentioned helium-3 on graphite, but you've obviously got helium-4 and helium-3 in their liquid states. So has anybody, I mean, there's a plethora of data, but it may not be in the right place.
That's a lovely question. I'm not aware of anybody calculating QFI for helium liquids, but if you've got dynamical structure factor data, of course you can do
I
that.
do, although it's a long time ago, so I have to do that.
No, that's a really nice idea.
Because I would have guessed that there are two Q points. There's Q equals 0 and there's the minimum of the
rotation. What you're thinking? Or,
yeah, exactly.
Yeah, no, it's a nice idea. I haven't looked at it.
But I'll try and dig it out and see, although it's a long time ago, so we may not have.
You might want to measure it again.
It's very easy to measure.
Yeah, exactly. I mean, maybe that's
There's
one of the first.
Nothing wrong with easy to measure. Unfortunately, for us, this is a bit of a nightmare. By the time that you've got quantum dynamics at finite temperature and disorder, you really are burning a lot of superconducting time.
Yeah, because obviously as a liquid, it's very disordered, but perhaps in a way that doesn't matter.
Well, helium is famous for not having disorder, right? So I would have thought that was a lovely example of what can we do with clean. Maybe even concurrence is back in play. If you take literally what the helium people tell you about there being no disorder, then maybe you can do something. I don't believe you're going to find a solid state sample so pure that you can do that, but maybe the helium.
Day one experiments on CSPEC. Okay. Thank you very much. It was very informative, and we see you again in 2 years' time. Okay.
Good.